Hello everyone, today we are continuing the topic in drainage design. Basically in this lecture, we will focus on the introduction about some materials applied for the drainage system. In general, there are three types of the drainage materials. The first one is aggregates. The aggregates can be used as one part of the pavement structure. Usually they will be used as the drainage layer or as the filter materials. The second one is geotextiles. Sometimes they will be used to replace the aggregates and applied as the filters for the drainage system. The third one, pipes, such as the perforated, slotted, or open-joined pipes. They are commonly applied for the drainage system to collect the waters and remove the waters from the pavement structures. For aggregates used as a drainage layer, they must have very high permeability to accommodate the free passage of water. Also, the aggregates will be used as the filters in the drainage system, so they must be protected from clogging to maintain their design function. So here you can see that the permeability is very important for the aggregates in the drainage design. Usually the permeability of one material is related to the grain size of the particles. The figure on the right shows the permeability of different materials with the various grain size distribution. Usually the permeability is defined as the variable little k, and the unit for the permeability is similar to the speed. We can use feet per day or centimeter per second. Clearly you can see that with the higher grain size, the permeability of the material will be larger. Generally, the fine particles can reduce the permeability of aggregates. So in order to obtain desired permeability, we want to remove the fine particles from the aggregates. However, we know that the gradation of one material ranged uniformly from coarse to fine is very critical for the stability of the material. So removing the fine portion from the aggregate will reduce the stability of the materials for the design of the drainage layers. In order to compensate the impact of removing fine particles, we want to introduce the treatment with a small amount of asphalt or Portland cement. The table here shows the permeability of untreated and asphalt-treated aggregates. In the table, you can see that by using the treatment with 2% of asphalt, the reductions about the permeability is very small. So we will still have an acceptable permeability for the aggregate. The table here summarizes the permeability of graded aggregates with no fines passing number 200 sieves. Clearly you can see that by reducing the amount of the particles with a smaller grain size, the permeability of the sample can be increased dramatically. For example, for the sample 1, the percentage passing number 10 sieve is still 39%, while the permeability is only 10. However, by removing all the small particles which can pass number 10 sieve, the permeability can be increased from 10 to 3000 for the sample 6. In addition, the percentage of the particles passing number 200 sieve can also dramatically reduce the permeability of the aggregates. For example, in this figure, if we increase the percentage of the particles passing number 200 sieve for clay from 0% to 25%, then the permeability will be reduced from 10 to less than 0.0001. This is a very huge reduction about the permeability of the aggregate. From empirical analysis, we can find that there exists some approximate relationship between the permeability and the grain size for one aggregate. One popular formula we will introduce here is the Hudsons Formula. In this formula, we define the permeability as the function of the grain size. Here, K equal to capital CK times D10 square. Little k here is the permeability in millimeter per second. And D10 is the effective size, which will usually be obtained as the grain size corresponding to 10% passing, and the unit for this one is a millimeter. Capital CK is the experimental coefficient depending on the nature of the soil. The unit for this coefficient is 1 over millimeter second. The table here shows some typical values of D10 and CK for some soils. For uniform sand, D10 varies from 0.06 to 3 millimeters, and CK is 8 to 12. If the value of the percent passing A and B percentage for two grain size, dA and dB, are given, then the size of dx for any percentage passing x percent between A and B can be computed with a linear equation here. So log dx equals log dA plus x minus A over B minus A times log dB over dA. With that, we can find out the grain size of any percentage passing based on two known grain size of given percentage passing. Now let's check how we can find out the effective grain size for the estimation of the permeability. In this example, we assume that 3% of minus 200 fines is added to sample 1 in the table 8.3, and we want to find out the value of D10. So here I pick up the part we want to use for this example from table 8.3. In this table, we can find that at different size of the sieves, there are different percentage. We want to find out the D10, which will be the percentage around 10% for this grain size. In order to find out the value of D10, we will call the equation in the previous page, which is log dx equal to log dA plus x minus A B minus A times log dB over dA. In the table, we can see that there will be several percentages for the sample 1, but there isn't any value about 10%. Instead, we can find 13% and 6%. So 10% is between these two values. That will be number 60 sieve and the number 140 sieve. The size for number 60 sieve is 0.25 millimeter, and for 140 it's 0.105 millimeter. Now we can assume that A equal to 6, and then dA is 0.105, B equal to 13, and then dB is 0.25. With that, we can find out the value of D10. That is log D10 equal to log dA is 0.105 plus 10 minus A is 6, B is 13 times log 0.25 over 0.105, which will give you the value as minus 0.907. So we can find out the value of D10 as 0.124 millimeters. So that's the way for us to use the equation to solve D10. There's another formula, Hudsons formula, to describe the relationship between the permeability and the effective grain size. This formula is usually applied for the granular drainage and filter materials. The formula here shows the relationship. Basically, K is a function of D10, N, and P20. Here, N is the porosity, which is computed as N equal to 1 minus gamma D over 62.4 times GS. In this equation, gamma D is the dry unit weight in PCF, GS is the specific gravity of the solids, and then P200 is the percentage passing number 200 sieves. Now let's check one example to see how we can use the Hudsons formula to estimate the probability of one aggregate. Here we assume that 3% of minus 200 fine is added to sample 1 in the table 8.3, which is summarized in the table here. We want to determine the probability with the Hudsons formula. Also, we assume that the specific gravity of the solid is 2.7, and the dry density increased by 3%. So, with that one, we will first list the Hudsons formula. We will have K equal to 6.214 times 10 to the power of 5 D10 to the power of 1.478 times n to the power of 6.654 over P200 to the power of 0.597. So here we want to get D10, N, and P200. From our previous example, we get a D10 is a 0.124 millimeter. And we want to find out N and P200. Also, we know that N is 1 minus gamma D over 62.4 times GS. So here we need to get a gamma D, GS, and P200. From the assumption, we will have GS is 2.7, which is given by the assumption. For gamma D, as the dry density, and we know that the dry density increases by 3%. The original dry density is 121. So that is 121 times 1 plus 3%, which is 124.6 PCF. And that one is actually equivalent to 19.6 kilonewton per meter square. And next we want to find out P200. So we add 3% of the fines which can pass in number 200 sieve. Then the percentage for the these fines in this in the sample would be 3% over 1 plus 3%. That is 2.91%. And then we can estimate the value of N. It's 1 minus gamma D. Gamma D is 124.6 over 620.4 times GS. That is 2.7, which will give you the value as 0.260. Eventually, we can apply all these values in the Hudsons formula, which will give you the solution as 1.92 feet per day. So that's the way for us to use the Hudsons formula to find out the permeability. We also have the equation to estimate the permeability of asphalt-treated materials. The linear equation here shows the relationship between the permeability and the three variables, PB, VA, and P number 8. In the equation, PB is the percentage of the asphalt cement by total weight of the sample. VA is the percentage of air voids by total volume of sample. P number 8 is the percentage by weight passing number 8 sieve, with the size of 2.36 millimeters. The aggregates can also be used as the filter in the drainage system. It's able to increase the drainage area, conduct the waterway, and hold in-situ soil in place. Usually the aggregates as the filter will be used for the earth dam and embankment, or is applied as the retaining walls. In general, we can use some granular soils or geotexture as the filter for the drainage system. There are two major criteria for us to choose filter materials for the design of the permeable base. The first criteria is called the retention criteria, which is also called as the clogging criteria. It's applied to prevent the washing out of the fine particles from the base. In that sense, the filter grain must not be too coarse, otherwise it cannot retain the fine particles. The second criteria is the permeability criteria, is used to facilitate drainage and avoid buildup of pore pressure. So the filter grain must not be too fine, otherwise the permeability will be low. In granular filtering design for drainage, the selections of the filtering materials should satisfy both the retention criterion and permeability criterion. For retention criterion, we want to make sure that D15 filter is less than 5 times D85 soil. Here, D15 filter is the grain size with 15% passing for the filtering material, and D85 soil is a grain size of 85% passing for the soil material. In addition, for permeability criteria, we want to make sure that D15 filter is higher than 4 times D15 soil. So with these two criteria, we can find out the upper and the lower bound of D15 filter. Also, for some design of the granular filter, the grain size distribution curve for the soil and the filter must be parallel. In that sense, we need to introduce an additional condition. D50 filter should be less than 25 times D50 soil. Moreover, Mountain also recommended that the amount of the fine passing through number 200 sieve must be less than 5%, or the D5 filter should be larger than 0.0029 inches, or that is 0.074 millimeters. Also, for highway design, usually we will choose the different values. For permeability, we want the D50 filter over D15 soil is higher than 5, not 4. And for retention or clogging criterion, we want the D15 filter over D85 soil less than 5. This is the same to the previous assumption. In general, for granular filter design, we want D15 filter over D85 soil less than 4 to 5, and D15 filter over D15 soil greater than 4 to 5. So let's see how we can choose the ranges for the appropriate filtering materials. So we assume that we are given the grain size distribution of the soil, which would be the blue line in this graph. And we can find out the grain size with 15% passing, that is 0.009 millimeters. Also, we can get the D85, the grain size of 85% passing, that is 0.11 millimeters. First, we're gonna use the same coefficient phi for both retention and permeability criterion. And for the permeability criterion, we want the D15 filter over D15 soil higher than 5. So 5 times D15 soil is the point here. And we want the D15 filter should be stay at a certain region on the left, which will have larger grain size. And then we can find out 5 times D85 soil. In that sense, we want to make sure that D15 filter be less than this value. So all the values on the right side of this line is valid. By combining these two boundaries, the soils with the grain size of 15% passing within this range will be appropriate for the granular filter design. So with that, we will have the gray region which are appropriate for the design. Now let's take a look at one example to see how we can choose the appropriate materials for the drainage design. In the example, we want to verify whether the open graded base with the permeability of 20,000 feet per day, that is 70 millimeter per second, which is showing the figure on the right. That's the line here. We want to check whether it's appropriate to place this base directly on the subgrade soil with a D15 as 0.0013 inches, D50 as 0.0055 inches, and D85 as 0.021 inches. If a subbase is to be placed between the subgrade and the open graded base, which of the filter materials shown in the figure can be used as the subbase? So here we have 5 options. The one with the permeability of 2 feet per day, 10, 20, 50, and 100. In order to check whether the base materials is appropriate for the filter on top of the subgrade soil, we need to recall the retention criterion and the permeability criterion, which means we have to find out the D15 filter and D50 filter. So that is D15, D50. Let's first go to check D15. So for D15, we need to find out the values from the figure on the right. So for the base materials that we choose, 20,000, it will be the straight line as we shown here. We can try to find out 2 distinct values in this line, which will be 1 point here and another point here. For the point at the bottom, we have the percentage of 1 and the grain size of 0.19. On the top, that is 32% grain size of 0.375. And next we can see that 15 is between 32 and 1. Then we can call the equation we proposed previously to calculate the value of D15. Here we get A equal to 1 dA equal to 0.19 and B equal to 32, dB equal to 0.375. With that, we can find out the value of D15 with the equation here. We assume that x equal to 15. So that is a log D1 plus 15 minus 1, 32 minus 1 times log D32 over D1. If you apply all the values that we received from the figure, then we can get the value about log D15 as minus 0.588, which will give you the value about D15 as 0.26 inches. Now we can apply the same process to find out value of D50 filter. From the figure, we can find out two sides of the particles, 0.5 and 0.75. Their passing percentage is 47 and 66. So we will have A equal to 47, dA is 0.5, B equal to 66, dB equal to 0.75. Then we can apply the same equation to get the value of D50. That is log D47 plus 50 minus 47, 66 minus 47 times log D66 over D47, which will give you the value as minus 0.273, and we can get the value of D50 as 0.53 inches. Now we can summarize all the information we already achieved. First, for the filter, which would be the base materials that we just calculated, we have D15 filter. The value is 0.26, and the D50 filter, the value is 0.53. In addition, from the assumption, we can get the information about the subgrade soil. So we have D15 soil as 0.0013, D50 soil as 0.0055, and D85 soil as 0.021. And first we're going to check the retention criterion. So we will have D15 filter over D85 soil. That is 0.26 over 0.021. It's 12.4, which is higher than 5, and that means the retention condition is not satisfied. And then let's go to check the permeability. We have the equation as D15 filter over D15 soil. That is 0.26 over the value of 0.0013, which will give you the rate as 200. That is higher than 5. So we say that the condition is satisfied for permeability. In addition, we want to check whether the grain size distribution are parallel to each other or not. So we have additional criterion, that is a D50 filter over D50 soil. So we have the value as 0.53 over 0.0055, which will give you the value as 96.4, and that one is much higher than 25. So we say that this additional condition is not satisfied. With this result, we say that the proposed base material is not suitable to be placed directly on subgrade. So that's the solution for the first question. Now let's see how we can get the second problem. In this problem, we assume that there's a subbase applied between the base and the subgrade. So we have a new subbase, and we have the base and the subgrade. We want to find out the appropriate filtering materials for subbase. So let's start with the subbase and the subgrade. The subbase is directly placed on top of the subgrade. So what we have is a subbase and a subgrade, and the one on the top will be filter. At the bottom, that will be soil. We know that for subgrade, we can get a D15, D50, and a D85. For subgrade, that is a 0.0013. D50 is a 0.0055, and D85 is a 0.021. We don't know the value about D15, D50, and D85. Actually, we want to find out the ranges of these three values for the subbase material. So now let's see how we can get these values, especially the range of these values. We will start with the retention criteria. So we know that D15 filter over D85 soil is less than 5. For now, I will just say that D15 filter it's just D15. I will just try to make it simple. And similarly, we will apply that one for D50 and D85. They will all be applied for subbase. So now we will have D15 less than 5 times D85 soil. That is 5 times 0.021, which will give you the value as 0.105. And we can call the second one permeability criterion. So we have D15 over D15 soil. It's higher than 5. So that is D15 is higher than 5 times D15 soil. We get 5 times 0.0013. So that is 0.0065. At last, we can check the additional criterion. That is D50 over D50 soil. It's less than 25. So that is D50 is less than 25 times D50 soil is 0.0055, which will give you the value as 0.138. Now we can check a base and subbase layer. The base layer is placed on top of the subbase. This means we will assume that the base is a filter and subbase is a soil. From the previous solutions, we can get a D15 filter for base and also D50. And we want to use this information to find out D15 for the soil, D50, and D85. So in order to find out these ranges, we want to call the criterion. The first one is retention. So we will have D15 filter over D85 soil, which we will just use D85 to simplify the calculation. This one should be less than 5. So we can derive this one as D85 is higher than D15 filter over 5, which will give you the value as 0.26 over 5 equal to 0.052. And then for the permeability, we have D15 filter over D15 soil higher than 5. That one will give you the relationship as D15 is less than D15 filter over 5. Similarly, get a value as 0.052. Finally, we will call the additional criterion. So we have D50 filter over D50 less than 25. That is D50 is higher than D50 filter over 25. So we have the value as 0.53 over 25 equal to 0.0212. So that's the conditions we gather from the base and subbase. From the results in the previous 2 pages, we can summarize the ranges for D15, D50, and D85 for the subbase materials. First, for D15, it should be larger than 0.0065 and smaller than 0.052. And for D50, should be larger than 0.0212 and smaller than 0.138. And for D85, should be larger than 0.052. As the last step, you will check the filter materials. And for all the materials which will satisfy these 3 conditions, they can all be applied for the subbase. Now let's see how we can find out the appropriate materials for the subbase. We're going to check the first condition for D15, which will be the line at the 15%. And we need to check the upper and lower bounds. The lower bounds is 0.0065, which will be someplace in between here. And you can find out the values between 0.0065 and 0.052. That will be someplace here. So any lines intercepted with this region will be considered as the valid material. With that, we can exclude the first one, K equal to 2 feet per day. And then for 50, so we have the line for 50, and then let's check the range. The lower bound is 0.0212. 0.0212 should be some place in between 0.017 to 0.023, and upper bound is 0.138. Should be some place in here. So with that one, we think the line with K equal to 100 will not be appropriate. And at the last, we will have the D85, which will be some points here. And D85 should be higher than 0.52. So 0.52 is a line here. Any place higher than this value should be fine. So all the lines satisfied. With that, we should say that K equal to 10, 20, and 50. These 3 types of materials are fine for the subbase. So we will solve all the problems in this example. So that's all about the lecture today. Thank you very much for your attention. In the next lecture, we will continue the topic in the drainage materials.